Hello everybody. We are TechPlayon team. We're here this time to talk to you about 5G new radio, which is making the waves in the industry. In this video, we will talk about 5G new radio introduction. After watching this video, you will have good knowledge about 5G technology evolution. What is 5G and why 5G is needed? 5G timelines and phase requirements of 5G technology. Wireless technology evolution started since 1980 with 1G amps technology, where user can do only analog voice call. Technology further evolved to 2G technologies like GSM and CDMA, where we got digital voice services in 1990s. The Internet was introduced in 1991 and world star changed with the demand of data services, which was not available with the 2G. Data service was introduced in 2.5G GPRS technology with 34 to 171 kbps, and 2.75G AGD service with data rate of 128 kbps to 348 kbps. Next generation of wireless communication was 3G with technologies like WCDMA, HSPA, EVDO, which are capable of providing both voice service as well as data services. 3G was able to provide somewhat 10 Mbps of data rates. Next we got 4G technology like LTE, LTE Advanced and WiMAX, which can provide data rates of 100 Mbps, LAN cable connected type capacity over the wireless link. 4G introduced the concepts of orthogonal frequency division, multiple access, and MIMO to achieve these high data rate. Now we are moving toward the application which need very high data rates, low latency, massive number of connected devices. These use cases include enhanced mobile broadband services, mission-critical services, and massive Internet of Things. All these use cases can be supported by existing 4G technology, so we need to evolve to a new technology named 5G, or a fifth generation of wireless communication. So now let's talk about what is 5G and why 5G comes into picture. 5G is a new wireless standard and foundation of fifth generation wireless communication, and it is given a name New Radio or NR. It is being developed part of continuous evolution of wireless broadband communication to meet the requirements of 5G outlined by IMT 2020, whereas LTE was developed as part of IMT 2010 requirements. IMT is International Mobile Telecommunication. New radio target is to make wireless network same as a wireless line network with fiber-like performance at significantly low cost per bit. So now question comes in mind that when we have LTE Advanced kind of technology which can support data rate of 1 Gbps, then why we need 5G new radio? And here is the answer. The lower bands below 5 GHz are completely occupied and now need to move to higher frequencies in millimeter wave band, so current technology like LTE, HSP were not designed to work on such higher frequencies. To support high data rate of Gbps we need larger bandwidths up to 1 GHz, and LTE and other technologies cannot support such huge bandwidths. 3GPP has started normative work for 5G, and it is planned for 2 phases. Phase 1 is S3GPP Release 15 to be completed by September 2018, whereas Phase 2 as Release 16 is to be completed by March 2020. Phase 1 is to address the more urgent and commercial needs, and during Phase 1 non-standalone NR is to be standardized. Phase 2 will address IMT 2020 requirements and to address all identified use cases with standalone NR standardization. Non-standalone NR means new radio is going to be deployed with LTE, where LTE is going to anchor the NR cell. Whereas in standalone NR deployment as NR cell can indecently work. Now we can move to the requirements for the 5G, and these requirements can be categorized as vision and service requirements, KPI requirements, architecture requirements, operational requirements, deployment morphology requirements. 5G vision and service requirement are driven from IMT 2020. IMT 2020 provided 3 use case and 8 performance benchmarks. The three use case includes enhanced mobile broadband, EMBB, massive machine type communication, MMTC, and ultra-reliable low-latency communication, URLLC services. EMMB includes applications like gigabit internet, 3D video, ultra-high-definition videos, VR and AR. MMTC includes services like smart home, smart cities. URLLC application includes self-driving cars, mission-critical application like health, industry automation, etc. Considering these three use cases, IMT come up with some performance benchmark, and about these will be discussed in coming 5G KPI slide. IMT 2020, considering these three use cases, comes up with the performance benchmarks or key performance indicators, that is KPI, and each KPI is associated with one use case. Like peak data rate requirement for downlink is 20 Gbps and for uplink 10 Gbps. This peak data rate requirement is associated with the MBB use case. So one can check the other key performance indicators like spectral efficiency, latency, user experience data rate, area traffic capacity, connection density, energy efficiency, reliability, mobility interruption time, system bandwidth support, coverage, and UE battery life. 5G is going to have a new network architecture, so 3GPP has set some requirements for it. The requirements are: new RAN architecture shall support tight interworking between the 5G and R and LTE. Different options and flexibility for splitting the RAN architecture shall be allowed. Architecture shall allow for C-plane and U-plane separation. New RAN architecture shall allow deployments using network function virtualization. New RAN architecture shall allow for the operation of network slicing. The design of the RAN architecture shall allow the deployment of new services, and that should be very rapidly and efficiently. Dual connectivity between LTE and new RAN shall be supported for co-located and non-co-located site deployments. RAN CN interfaces and RAN internal interfaces shall be open for multi-vendor interoperability. Along with network requirements, the standardization bodies has set operational and supplementary services requirements, and these are as follows. NR shall support channel bandwidth scalability, spectrum flexibility, and duplexing flexibility. NR shall support spectrum range up to 100 GHz. It shall support self-organization networks along with security and privacy-related, relevant for radio access performance monitoring and management. NR shall support supplementary services like multimedia broadcast multicast service, location positioning service, public safety communications, emergency communications, and public warning or emergency alert systems. As 5G has different use cases, so it is going to be deployed in different kinds of environment. It can be highly indoor for MMTC smart parking system application, where parking can be second or third basement, or an urban city with application like gigabit internet services using virtual reality application. So 5G is required to work in all type of morphologies including urban, dense urban, rural, high-speed rain, etc. Some of the major deployment morphologies considering the three use case are pointed here. Like indoor spot morphology, which focus on small coverage per site, and need to cater high user throughput or user density in a building or in a house. So one can see other morphologies here, like dense urban, rural, urban macro, high speed, extreme rural for the provision of minimal services over long distances, extreme rural with extreme long range, urban coverage for massive connection, highway scenarios, urban grid for connected cars, etc. Concluding this presentation, we have covered 5G technology evolution, what is 5G and its timelines, and we have also covered 5G technology requirements. In future, we will be covering more topics on 5G. So stay tuned till then, and please do not forget to follow us on social media. Thank you.
In this video, we will try to understand various physical layer waveforms in general, and then we will try to find out why cyclic prefix based OFDM waveform is used for the 5G new radio standard. Goals of this presentation are listed here. First of all, we want to understand the underlying motivations for understanding various waveforms. Then we will compare various waveforms which are discussed for 5G new radio, and in the end, in particular, we will compare the filtered OFDM with the cyclic prefix OFDM. So first of all, let us define what are the different use cases and the technologies involved in the 5G new radio. In regard to the use cases, first and foremost is the enhanced mobile broadband, and here we are addressing human-centric use cases. So these are related to the high data rate and large bandwidth. For example, access to high throughput multimedia content. The second is ultra reliable low latency communication. Here we have the strict requirement in terms of the latency and reliability. So we are talking about the use cases like connected cars, drones, and mobile robots. In a way, we are talking about two conflicting requirements, because we want low latency and high reliability. This makes the physical layer design, in particular waveform designs, complex. The third is the massive machine type communication, and we are talking about very large number of the connected devices. And then in terms of the technologies, there are massive MIMO and beamforming. So the number of antenna elements in the base station and devices are increasing, and we have the high frequency spectrum, for example millimeter wave. So keeping in mind the use cases and the technology involved, we need to understand the certain key performance indicator for a physical layer waveform. Let me start by saying that for any radio access technology, one of the deciding factor is its underlying waveform. For example, GSM uses Gaussian minimum shift keying, and it has a characteristic of the constant envelope, and which has its own advantages like excellent power efficiency and high spectral efficiency. Likewise, LT uses classic CP based cyclic prefix based OFDM waveform, and it has advantages like it is robust against frequency selective fading, the channel equalization is simpler. So if we define these performance indicators, there are some of them are listed here. First is the spectral characteristic of the waveform, and that can be further divided into spectral efficiency and spectral localization. So the waveform should be such that the spectrum is utilized fully. There is no waste of the spectrum. And localization can be further divided into two categories. One is time localization, another is frequency localization. For good time localization is required in order to enable the low latency, especially in a adaptive TDD system with the need of fast and flexible switching between the downlink and uplink. The waveform needs to enable this short switching time between downlink and uplink. Then another performance indicator is the multi-antenna support by the waveform. MIMO system depends on the knowledge of the channel or the channel state information. In the practical system, channel is not known to the receiver, So channel estimations are done. So the channel state information is not perfect. So it should be analyzed what is the impact of the imperfect channel state information on the performance. So for various physical layer waveforms, what is the impact on the performance because of the imperfection in the channel state information? It all also depend on the whether there is a cyclic prefix or needed or not needed in the underlying waveform, because that introduction of the cyclic prefix somehow reduces the interference, but in another way it also reduces the spectral efficiency. The third performance indicator is the power. So the waveform should not be power hungry. There should be low peak to average power ratio requirement. Also, the power amplifier linearization is a very important criteria, because in the real systems we have to consider the low cost design of the power amplifier which work in the power amplifier linearization linear zone. The fourth is the complexity of the baseband system. So as we move forward the 5G radio access technology, the algorithms are becoming complex. So the underlying waveform itself should not add to those complexities. For example, the equalizer design in the receiver or in the transmitter complexity should not increase just because of the underlying waveform. The other performance indicator is the robustness against the RF impairment. For example, phase noise. So the low noise phase oscillators are costly, and therefore it is important the underlying waveform should have the robustness against phase noise and in general all the important RF impairments. The other important performance indicator is robustness against the synchronization error, for example time and frequency. So now based on this background, let's try to understand what is the underlying motivation to study other waveforms. The CP based or cyclic prefix based OFDM which is used in LTE today has certain drawbacks. First is that it has the high level of out of band emission. So in OFDM the shape of the used sync pulse in frequency domain results in the out of band emission, which causes strong interference into neighboring frequency bands. And if we see the 5G use cases like massive machine type communication and ultra reliable low latency communication systems are impacted by this drawback. The other thing is the one of the requirement is that we minimize the leakage of the power outside the very narrow guard band around the useful signal band. But in OFDM there are large side lobes which causes to reduce the spectral confinement and also reduces the occupied bandwidth. For example, in LTE the maximum occupied bandwidth is 90% of the allocated channel bandwidth. So if you have 20 megahertz channel, only 100 RBs are used, which is the 90% of the allocated possibly allocated channel bandwidth. This is also again impacts the MMTC and ultra reliable low latency communication use cases of 5G. Third is the sensitivity to the carrier frequency offset and long round trip delay time. So if you are talking about low latency systems, and if the waveform itself has a long round trip time and it is sensitive to carrier frequency offset, then it impacts both the use cases, which is ultra reliable low latency communication and enhanced mobile broadband. The fourth and important is that CP based OFDM waveform has high peak to average power ratio. So it becomes very difficult to design cost effective power amplifier, especially for massive MIMO system, and it affects or impacts most of the 5G new radio use cases, which is ultra reliable low latency communication, enhanced mobile broadband, and massive machine type communication. With this knowledge, let's try to understand the cyclic prefix based OFDM signals drawback using this web demo, which is available at the website of the University of Stuttgart. In this web demo, we can define the number of subcarriers, length of the CP, and we can plot in three different ways. We can plot PRB wise, in which we can define number of subcarriers within PRB and number of PRBs. Subcarrier wise plot, we can define number of subcarriers, and for allocation wise plot, we can define number of allocated subcarriers. For plot itself, we can plot in time domain, frequency domain, or both. So maybe we'll stick to frequency domain for this demo. Okay, maybe we'll plot subcarrier wise, and I will give only 2 subcarriers. Define CP length of 100 samples. So now we can see that this is the representation of the OFDM signal in frequency domain. The subcarriers, I have taken 2 number of subcarriers, so these are closely spaced subcarriers and they are overlapping with each other. But that is not a problem because these subcarriers are orthogonal, which means that if we see 2 adjacent subcarriers, in this case there are 2, only 2, and this red one and this blue one. These are the peaks of the subcarriers, and the peak of this subcarrier is aligned with the null of the adjacent subcarrier, which means they are orthogonal and there is no intercarrier interference. The subcarriers will interfere with each other only if there is a loss of orthogonality. For example, if there is a frequency error, that will cause the subcarrier frequencies to shift, and in that case the peak of this subcarrier will not align with the null of this subcarrier, and this will result in the loss of orthogonality, and it will result in the inter subcarrier interference, and this is one of the drawback of the cyclic prefix based OFDM. Also, another drawback which we saw is that the cyclic prefix OFDM has a large number of side lobes. So these are the side lobes, and these are the main lobes. So this is again a drawback because we don't want to leak the spectral power. Now let's look at some of the examples of 5G NR waveform which were analyzed. So some of them are listed here. Mainly there are 4 waveforms. First is obviously the classic CP based OFDM waveform, which is used today in LT system. And if you look closely, all the waveforms are related to the filtering. Only difference is how and where that filtering is applied. So in case of CP based OFDM waveform, the rectangular filter is used, and that filter spans over total number of subcarriers. In case of generalized frequency division multiplexing, there is a pulse shaping filter is used, and this filter is applied or spans over per subcarrier. In universally filtered multicarrier waveform, the filtering is applied over a band of subcarriers. So the multiple subcarriers form a band, and over which this filtering is applied. In filter bank multicarrier waveform, the polyphase filter banks are used for pulse shaping, and filtering is applied per subcarrier basis. So if we see the comparison of these waveforms, which I have taken this table from this IEEE paper, and it summarizes the differences between these waveforms. For example, in case of OFDM waveform, the filter granularity is whole band, and the length of the filter is also an important factor, which is generally less than equal to CP length in case of OFDM. And OFDM signal is orthogonal in time and frequency, but it has a problem of out of band emission. Then there is a generalized frequency division multiplexing, where the filter granularity is over subcarriers instead of whole band. Here the filtering spans over subcarriers, and the filter length is more than the less than equal to CP length. Here the filter length is greater than symbol duration, and we are talking about completely a different kind of waveform, where the waveform is non-orthogonal in time and frequency. But one advantage of using this waveform is that out of band emission is good, which means there is not much out of band emission. Other is the filter bank multicarrier waveform, where the filter granularity is subcarrier wise, but the filter length is increased, sometimes more than 3 or 4 times symbol duration, and these are orthogonal in real domain only. But best part is that the out of band emission is best in this case. There is a universally filtered multicarrier waveform, in which case also the filter granularity is subband, and this has shortest filter length, so it is equal to the CP length. These are orthogonal in the time domain and quasi orthogonal in the frequency domain, and the out of band emission is good. Then there is another class of waveform which is called filtered OFDM, in which case the filter granularity is subband, and the filter length is still high. It's around less than equal to half of the symbol duration. It is again in time domain it's non-orthogonal and quasi orthogonal in frequency domain, and it has a good out of band emission. This is another way of looking at the comparison among various waveforms. These are probably the performance indicators we actually saw earlier. For example, there is a peak to average power ratio, which is very high in case of CP-OFDM, and it is moderate in case of generalized frequency division multiplexing. Similarly, the spectral efficiency, which is very low in case of the CP-OFDM, and it is very high in all other cases. Overhead in terms of the adding CP, it is high in CPU FDM. FBMC doesn't require any CP, so there's a low overhead. Similarly, in the case of GFDM, shorter length of the CP is required, so there is a variable overhead. Also, UFMC doesn't require CP, so the overhead is low. Out of band emission we already saw. The computational complexity is another important factor, and which is very low in case of the OFDM, and all other cases it is high. Other equalization is same, revolves around the complexity, which is simple in case of the cyclic prefix OFDM, but it is very involved in case of filter bank multi-carrier waveforms. And resource allocation is dynamic and fine-grained in cyclic prefix OFDM, and it can be configured in all other cases. One other important factor is short bus traffic, which is required for the machine type communications or ultra low latency type of communication, which is not there in the CP based OFDM waveforms, and also in the case of filter bank multi-carrier waveforms, but it is there in generalized frequency division multiplexing and universally filtered multi-carrier schemes. And fragmented spectrum, in CP OFDM there is no fragmented spectrum. In all other cases there is a fragmented spectrum. Layer 1 latency is also high in CP based OFDM and FBMC case. It is moderate in case of GFDM, and UFMC case it is very low. If we see all these comparisons, this one and this slide, we see that there is no clear winner. In some cases, for example, spectral efficiency is low in CP OFDM, and FBMC all other cases high, but the complexity is high in all other cases, but CP OFDM has a low complexity. So there's no clear winner in all these waveforms. So keeping in this mind, 3GPP has chosen CP based AFDM for the release 15 candidate, and in August 2016 it agreed to adopt CP OFDM for both uplink and downlink in 5G. Also, one important thing to note that CP based OFDM waveform was used in LT only in the downlink direction, but now it will be used in both uplink and downlink direction, so it will play a greater role in 5G neo radio compared to the 4G LT. Okay, now let's see this comparison a little bit. For example, here the same website from the University of Stuttgart compares the filter bank multi-carrier waveform, a class of that kind of waveform versus the classical OFDM. And we can see here, if I compare this only in frequency domain with the OFDM, yeah, we can see that the maybe just the subcarrier wise plot, and maybe I will have only two. Yeah, so here we can see that the roll off is very quick in case of the FBMC, and in case of the OFDM the roll off is not very quick, and that makes a good amount of difference in so this is it all about the 5G waveforms and how the selection was done. We didn't go through the entire details of the each scheme, but we just wanted to compare all the waveforms. That was the intention of this presentation, and thank you for watching.
Hi everyone, welcome to our new video on 5G NR modulation and coding schemes. In this video, we will discuss about the modulation coding scheme or say MCS used in 5G. Let's start with the basic definition and some characteristics of modulation and coding scheme. So modulation and coding scheme basically defines the number of useful bits which can be carried by a symbol. In contrast with 5G or 4G, a symbol can be defined as a resource element or RE and MCS defined as a how many bits can be transmitted per resource element. In any wireless link, MCS depends on the radio quality. Better the radio quality, higher the MCS. And this higher MCS means we have more useful bits which can be transmitted in a symbol. And bad signal quality result in a lower MCS, which means we can transmit less useful data within a single symbol. So MCS also depend on block error rate or say blur other than the signal quality. Typically, there is a threshold for blur for every MCS and this is usually 10%. To maintain this blur, the base station or say GNB in 5G keep on changing this MCS based on the radio conditions. And this MCS is communicated to the UE using DCI, which is downlink control information over PDSS channel. In 5G we have like DCI 1011 which is used for MCS signaling. A MCS basically defines two properties. The first property is modulation and second property is code rate. So let's discuss about modulation and code rate in next slide. Modulation. Modulation defines how many bits can be carried by a single resource element irrespective of whether it is a useful bit or parity bits. 5G NR support QPSK, 16 QAM, 64 QAM and 256 QAM for data channel or say PDSS channel. With QPSK, there are 2 bits can be transmitted per resource element. With 16 QAM, it can be 4 bits. With 64 QAM, it can be 6 bits. And with 256 QAM, it can go up to 8 bits per resource element. This 16, 64 and 256 are known as modulation order of QAM modulation. The number of bits for each modulation order can be calculated using the shown formula. The 2 raised to power n equal to modulation order. So for 2 raised to power 4 equal to 16. So this n represents here the number of bits. So 2 raised to power 6 equal to 64. Means 64 QAM, 6 bits. 2 raised to power 8 equal to 256. And 2 raised to power 10 is 1024. So if we say QAM order is 1024, it means one resource element can carry 10 bits. The second property of modulation and coding scheme is code rate, or we can also say coding rate. So code rate can be defined as the ratio between useful bit and total transmitted bit. And this total transmitted bit is useful plus redundant bit. These redundant bits are added at the file layer for the forward error correction. In other words, we can say that the code rate is the ratio between the number of bits at the top of physical layer and the number of bits which are actually transmitted or mapped to the PDSCS channel at the bottom of the physical layer. So on the right side, we can see this diagram. So here we can see we have n number of bits at top of the physical layer, and after adding this redundant bit, this becomes n plus k. And then these bits, n plus k bits, are mapped on the PDSCS channel. So code rate here will be n divided by n plus k. This one. The code rate is a measure of redundancy which is added by physical layer. A low code rate result into high redundancy. Here we can also see a calculation for the code rate using a table from 3GBP. So this table is basically MCS table from physical layer spec. So we can take very first this particular row where we can see 120, and this 120 is actual bits, whereas the total bits transmitted for this modulation is 1024, this much, and the code rate for this comes as 0.117. MCS tables. In 4G, we were having only single table for MCS for PDSCS channel. But in 5G, we have these three tables for different applications. And I have taken this MCS table from physical layer spec 38.214. So we can see at the bottom of each table we have given some name. So very first table is 64 QAM table, and this is similar to your LTE table. Then second table is 256 QAM table, And as per this table, the maximum MCS can go up to 256 QAM with certain code rate. And the third table is for low spectral efficiency table. So this third table is specifically used for applications which require reliable data transmission and low latency communication. So as per 3GPP use case, this table is very suitable for ultra reliable low latency communication. So in each and every table, we can see the MCS starts from 0 and it go up to 31. So total number of MCS indexes are 32. We can also see here that some of the modulation are shown as reserved, like this 29, 30 and 31 in first table and the third table. So these modulations are reserved for the retransmission, whereas other modulation indexes can be used for normal data. In next slide, we will discuss in what condition the E node B or UE will choose which modulation table. The MCS table selection in 5G can be controlled by E node B using RRC signaling and physical layer signaling. As part of RRC signaling, the E node B sends specific configuration for this MCS table, and the physical layer can control this using MCS CRNTI. Let's take first 256 QAM table example. So we have two cases for this MCS selection related to 256 QAM table. The first case is the dynamic scheduling, and the second case is semi-persistent scheduling. In dynamic scheduling, E node B sends PDSH config as part of RRC signaling, and under this PDSH config, it indicate MCS table which is QAM 256 for 256 QAM table selection. And here the UE will be scheduled with DCI 1_1 with CRNTI. For second case, in SPS scheduling, when the RRC set SPS config without any MCS table and PDSH config with MCS table as QAM 256. Here the UE is scheduled using DCI 1_1 and CSRNTI, or UE can be scheduled without DCI using SPS config. The second table we can take is low SC table. This low SC table also QAM 64 low SC table, and selection of this table can be done using RRC signaling or physical layer signaling. For physical layer signaling, UE has to be configured with MCS RNTI as well as the CRNTI. And the scheduling for this UE is done with the MCS CRNTI. Here also, we can have two cases like dynamic scheduling and the SPS scheduling. In dynamic scheduling, when the UE is not configured with MCS CRNTI, then E node B send RRC signaling including PDSCH config indicating MCS table, and this MCS table has to be QM64 low SC for this table selection. And in this case, UE has to be scheduled with CRNTI. As there is no MCS CRNTI allocated, SPS config is used for semi-persistent scheduling, and this SPS config shall include MCS table indicating the table choice. And in this case, the UE is scheduled with CS-RNTI when using DCI, and when we are not using DCI, it can be scheduled with SPS config. And if we are not able to match the first case and the second case, the by default that it can use the third table, which is 64 QM table. Let's now discuss about MCS table selection with an example. So in this example, we will see how physical layer signaling can control this MCS table selection once initial RRC signaling has been done. So let's consider a UE which is configured with parameter PDSCH config with MCS table as QM256, and it has been allocated MCS CRNTI along with traditional CRNTI. If the UE receives a PDSCH resource using DCI 1_1 with CRNTI, then UE will select 256 QAM MCS table. If the same UE receive PDSCH resource using DCI 1_0 with CRNTI, then this UE will select 64 QAM. So we can see here, just by changing the DCI format from 1_1 to 1_0, the MCS table is changed from 256 QAM to 64 QAM table. If the same UE receive a PDSCH resource allocation using either DCI 1_1 or 1_0, but with the MCS CRNTI, so in this case, the UE will select low spectral efficiency table. So here the table selection does not depend on DCI, but it depends on MCS CRNTI, and this MCS CRNTI indicate UE to select low spectral efficiency MCS table. So here we end this topic. So thanks for watching this video. If you like this video, please like it, share it, and don't forget to follow our channel for next videos. Thank you very much. Have a good day. Hi everyone. Welcome to our new video on 5G frequency band. In this video, we will discuss about the frequency bands specified by 3GPP for the 5G applications. So let's start. So here in this slide, we can see the frequency range defined by 3GPP for 5G. So very first time the 5G standard was defined in release 15, and there they defined two frequency range which can be utilized for 5G NR services, and this frequency range are basically FR1 and FR2. So FR1 are the lower frequency range, or we can say in the lower bands, and their frequency range defined from 410 to 7125 MHz. Whereas the FR2 frequencies are in the higher bands. These higher bands are also known as millimeter waves bands, and their frequency range is starting from 24 GHz to 52 GHz. At the bottom of this like the frequency scale, we can see some cell sizes with the different colors. When we see the yellow ones, so the yellow ones are the larger cell size, so which indicate the FR1 frequencies belongs to lower bands will give larger cell size, and 5G services within this frequency range can be utilized for the coverage. And as we go with the higher frequencies, the cell size shrink. So if we see the green color, so green color basically represents the millimeter waves, and in the millimeter waves the cell size becomes very small. But the benefit with the millimeter waves is we have larger bandwidth, and with the larger bandwidth we can get the large capacity. So as we go in the higher in the frequencies, we can get a larger capacity, and if we go on the lower bands, there the bandwidth will be less, so those bands can be basically utilized for the coverage requirements. Let's go into the deeper detail of frequency ranges. As per 3GPP, there are two frequency ranges defined for the 5G. The one is frequency range 1, which is also known as FR1, and second is frequency range 2, which is also known as FR2. The FR1 range starts from 410 to 7125 MHz. This is also known as sub 8 GHz range, and it is suitable for continuous coverage, high mobility and reliability, because these are the lower frequencies and which has lesser attenuation and the path loss. The maximum available bandwidth within FR1 is 100 MHz. As we know, the 5G support different subcarrier spacing, and within FR1 we can use 15 kHz, 30 kHz and 60 kHz subcarrier spacing. The bands available within frequency range 1 can support FDD, TDD, supplement downlink and supplement uplink duplex mode, which means they are capable to support all duplex modes. When we come to frequency range 2, so their range starts from 24 to 50 MHz to 50 to 600 MHz. This frequency range also known as millimeter waves because their wavelength is into the millimeter orders. The FR2 is suitable for high capacity and higher throughput. The maximum available bandwidth within FR2 is 400 MHz, which is like 4 times larger than the FR1. The FR2 support subcarrier spacing starting from 60 kHz to 240 kHz, and FR2 only support TDD duplex mode. They cannot support FDD and other duplex mode. They are only available for the TDD duplex mode. In previous slide, we discussed something about the duplex mode. So to get more information on the duplex mode, we first need to understand the link directions. So here we can see we have a base station, say GNB, and we have a mobile device, we say this is a UE. The signal transmitted from the base station towards the UE are known as downlink. And the signals which are transmitted from UE to base station are known as uplink. So keeping this in mind, in further slide we'll discuss about the different duplexing used in the 5G. In previous slides we discussed that FR1 frequency range can work with different duplex modes, and some of these duplex mode we'll be discussing in this slide. So let's start with the FDD duplex mode. So FDD means frequency division duplexing. So in FDD, what we have from this picture, we can see there are some downlink transmissions and there are some uplink transmissions. The downlink transmission, which is noted by DL, and they are happening on the F1 frequency, and the uplink transmission which happens on F2 frequency. So it means in FDD duplex mode we will be getting two frequencies which can be used for downlink and uplink at the same time. Further going to the TDD, TDD is time division duplexing, which means we'll be using the frequency F1 at different times. By looking on this particular section of the diagram, we can see at T0 frequency F1 is used for downlink. At T1 time, the same F1 frequency is used for uplink. At time 2, the same frequency is used for downlink again, and at time 3, this frequency F1 is used for uplink. So we have only one frequency, and this frequency is shared between uplink and downlink at different times. The third duplex mode which is available in the 5G is SDL. So STL is supplement downlink. So in SDL there will be one frequency and that will be always used for the downlink. So STL is basically used to increase the downlink capacity. Then the fourth duplex mode supported in the 5G is SUL. So SUL is supplement uplink, where the frequency is used for uplink transmission. Five G frequency band classification. 5G NR operates in FDD, which is a paired spectrum, and TDD, which is an unpaired spectrum, similar to the LTE. The 3GP release 38.104 listed all the bands which can be used for the 5G. The NR has introduced a new notation mechanism for the frequency bands. We start with the N. For example, the band 5 is noted as N5 in 5G, whereas in 4G it was noted as B5. So from B2 it becomes N. So NR bands can be classified into three categories. The very first category is the FDD bands, which we can say the paired bands. We say these bands pair band because we get frequency location in pair, means one frequency for downlink and second frequency for uplink. The second category for 5G bands is TDD bands, or we can say time duplexing bands. And the third category for NR band is supplementary bands. The supplementary bands which are used for the capacity purpose. The supplementary bands are further classified based on the direction, whether those supplementary bands are used for downlink or uplink. The bands which support the downlink are known as supplementary downlink bands, or say SDL, and the bands which can be used for uplink are known as supplementary uplink bands, or we can say SUL. So SDL bands are used for increasing the downlink capacity, and SUL bands are used for increasing the uplink capacity. In this slide, we have noted some sample bands for the 5G. We can see the FR1 band and FR2 bands. So FR1 bands, we can see N1, N3, N20, N38, N41, N51. There are some are newly introduced frequency bands and some are used from legacy technologies. For example, the LTE band 3, which is B3, reformed here with N3, and the frequency range is also the same. In FR2, the frequency band numbering start from higher order. For example, the frequency band number 257, or frequency band number 258, or 260. These frequency bands are in millimeter waves. We have also noted here the duplex mode for the bands. If we see the FR1 duplexing, they support FDD, TDD, supplementary downlink, supplementary uplink. But if we look into FR2, they only support TDD. In the same statement we gave in the previous slides. Frequency channel bandwidth. So frequency channel bandwidth defines how a band can be used with the maximum channel bandwidth. We discussed that frequency range 1, which is FR1, can have maximum bandwidth of 100 MHz and FR2 can have maximum bandwidth of 400 MHz. Within FR1, 3GPP has defined that channel bandwidth can be starting from 5 MHz and it can go up to maximum 100 MHz. One thing to be noted here that the 5G does not support lower channel bandwidth which are specified in LT. So LT was able to support 1.4 as well as 3 MHz channel bandwidth. But 5G channel bandwidth start from minimum from 5 MHz. For FR2, the minimum channel bandwidth can be 50 and it can go up to 400 MHz. There is some availability of larger bandwidth in the FR2, say for example 800 MHz. If any operator which is allocated 800 MHz bandwidth, so he cannot use 800 MHz as a channel bandwidth. What he has to do is he has to split this channel bandwidth into two carrier elements and then he can use that 800 MHz as carrier aggregation by using 400 MHz bandwidth with the two carrier components. Thanks for watching this video. Hope you like it. Please like this video and subscribe our channel for the upcoming information on the 5G. Thanks for your time. Hi, welcome to our new video on 4G 5G networks spectral efficiency. So in this video we will discuss about the basic definition of spectral efficiency. We'll do some calculation of taking some example, and as an outcome of this video or this session, we will calculate the spectral efficiency for 4G LT network as well as the 5G new radio networks. So let's start. Let me start with asking you a simple question. So what do you think when you hear the word spectral efficiency? So spectral efficiency is nothing but the amount of information that can fit in a given channel bandwidth, or one can say like how efficiently a piece of spectrum can be used to transmit information or to transmit some bytes of data. Spectral efficiency is usually expressed as bits per second per hertz, or we can say this is a measurement unit for spectral efficiency. So from these units we can clearly see that it's a measure of bits, how many bits can be sent within a second using a 1 hertz of bandwidth. So here we have noted a mathematical expression for spectral efficiency. So spectral efficiency can be defined as the net data rate in bits per second divided by bandwidth in hertz. So net data rate and symbols are related to the raw data rate, which includes the usable bits as well as the overhead. So using this mathematical expression, we can come with the three equations. These three equations are listed here. So very first equation is related to the raw data rate, which is a payload plus overhead. If we want to get the net data rate, so we can just simply deduct the overhead from the raw data. So then using the net data rate, we can calculate the spectral efficiency, and this can be net data rate in bits divided by channel bandwidths in hertz. So from the equation number 3, we can calculate the spectral efficiency. Let's take an example to calculate the spectral efficiency using the formula we discussed in a previous slide. In this example, I have taken channel bandwidth as 2 megahertz, and it can support a raw data rate of say 15 Mbps. Assuming 2 Mbps as overhead, then net data rate can be calculated as about 13 Mbps. So this net data rate is calculated by deducting this 2 Mbps overhead from the raw data of 15 Mbps. So let's putting all these uh, net data rate and the channel bandwidths in the spectral efficiency formula. So this is my net data rate, and this is my channel bandwidth, and doing the calculation, I can get like 6.5 bits per second per hertz as a result of spectral efficiency. So which means every second I can get 6.5 bits within 1 hertz of channel bandwidth. So after having hands-on on the formula, the spectral efficiency formula, we can go ahead with the calculating the spectral efficiency for 4G LTE network. So here I'm considering a 4x4 MIMO system, and theoretically the raw data rate for 4x4 MIMO system is about 400 Mbps. So assuming 20% as overhead uh, in LTE, so this overhead is because of this system broadcast information, your sync signal like PSN and SSS, then net data rate will be about 300 Mbps. So similarly we can be considered for the uplink, but we need to keep in mind that in uplink there is no MIMO support from the UE side, because UE has only one transmit antenna. It can have multiple receive antenna, but most of the UE has a single transmit antenna. So the maximum raw data rate for uplink can be 100 Mbps, assuming 64 QAM support in uplink. And similar to downlink, if we deduct 25% overhead in uplink, which could be because of your RAS channel, or because of your uplink control channel, then uplink net data rate will be about 75 Mbps. and assuming 16 QAM as maximum uplink modulation, then we can say that 51 Mbps can be net data rate. So we got these values, and we can simply put in the spectral efficiency formula. So downlink spectral efficiency can be calculated here. So this 300 Mbps is the net data rate, and I have taken 20 Mbps megahertz as channel bandwidth. So using this, we can get a result as 15 bits per second per hertz. So in downlink with the LT, we can get 15 bits every second with every hertz of channel bandwidth. So 64 QAM spectral efficiency we can calculate here. So I have taken the net data rate as 75 Mbps, and channel bandwidth is same 20 megahertz. So here we can get the spectral efficiency as 3.75 bits per second per hertz, and for 16 QAM the spectral efficiency is about 2.55 bits per second per hertz. So after calculating 4G spectral efficiency, we can now calculate 5G new radio spectral efficiency here. So I have kept a table, and in this table we can see some of the results for maximum throughput achievable with the subcarrier spacing of 15 kilohertz, 30 kilohertz, 60 kilohertz. And here I have taken maximum as 4 layers transmission using a single carrier. I'm not considering any kind of carrier aggregation in new radio, and modulation order which is QM considered here is 8, which relates to 256 QAM. So these throughput numbers shown in the table are calculated using this particular formula, and this formula is taken from 3GP specification 38.306 version 15. So for my calculation, I will be taking this 60 kilohertz subcarrier spacing, where we can achieve maximum downlink throughput as 2.31 Gbps and 2.47 Gbps in uplink. So here I have taken the channel bandwidth as 100 megahertz. So keeping this data rate values and channel bandwidth in spectral efficiency formula, for downlink we can get about 23 bits per second per hertz, and for uplink we can get 24 bits per second per hertz. Please mind that these calculations are purely theoretical. I have not taken any practical consideration here. So this is purely on the theory base, using some mathematical calculations. So as a conclusion of these spectral efficiency calculation, so we can clearly see that 5G is more efficient in terms of this spectrum utilization, because if we compare downlink of LTE and downlink of 5G here, so we can clearly see that from LTE was able to give the spectral efficiency as 15 bits per second per hertz, in the downlink, where with the 5G I'm able to achieve 23 bits per second per hertz. And here I have taken an transmission of 4 layers. So in LT also I have taken 4x4 MIMO, and in 5G also I have taken 4 layers. But 5G is capable to support even more layers, or we can say uh, higher order of MIMO. So then spectral efficiency will also increase with increase in the MIMO order. So here I have conclude my video, and thanks for watching this video. If you like, please share with your friends, and if you have any question, please put in the comment section. We will try to answer. Thanks for watching. Have a good day. Hi everyone, welcome to our new video on SS-RSRP measurement in 5G NR. In this video, we'll try to understand the SS-RSRP measurement which are done by the UE in 5G and used for the various procedures. So let's get started. The RSRP is reference signal received power. RSRP measurements is done by the UE. In 5G, UE does the measurement of SS-RSRP for the cell selection, cell reselection, power control, mobility, and beam management procedures. The RSRP measurements are generated and reported at 2 layers in 5G. And these 2 layers includes our layer 1, which is physical layer, and layer 3, which is RRC. For an example, UE can measure the SS-RSRP at layer 1 when it is sending the CSI reports. The CSI reports includes the CQI measurements, your RI measurements, and other measurements which are related to the layer 1. And base station can provide the SS-RSRP measurement results at layer 3 when it is sending the measurements reports. And these measurements reports can be used for the mobility procedures like handover and the beam mobility. In 5G, UE is allowed to measure the PBCH DMRS to generate the SS-RSRP results. Here, the DMRS and the SS signals are transmitted with equal power so that they can be averaged directly. When UE is measuring the SS-RSRP for layer 1 reporting, then UE can be configured to use CSIRS. CSIRS are basically channel state information reference signals and can use the additional inputs in terms of offset. If CSIRS have different transmit power compared to SS signals and the PBCH DMRS signal, then E node B or the GNB in 5G can provide the offset information to the UE so that can be taken into account for the measurement procedures. In this slide, we have captured some of the key pointers for SS-RSRP. So SS-RSRP is in average of power received from a single resource element allocated to the SS signal. And this averaging is done by calculating the linear power in milliwatts instead of doing average in dBm. This power is measured on the energy received during the useful part of symbols, and it does not include the cyclic prefix, which is an overhead of symbol. For FR1, which are low frequencies, the measurements is performed at the UE connector, and this is done by assuming that UE has a single antenna per receive path instead of an antenna array. For FR2, which has higher frequencies, or we can say millimeter waves, this measurement is performed based upon the combined signal strength received on the all antenna ports. And here this assumption is that UE has an array of antenna on each receive path. These measurements are done and filtered at two layers as we discussed in our previous slide. And these filtered measurements are done at layer 1 and layer 3. The SS-RSRP at layer 1 measurements are useful for the procedures like beam management, which require UE to rapid switch between the beams. The 3GP specification 38.133 defines the mapping between the reported value and the measured value for the layer 1 and layer 3 RSRP. As per the 3GBP, the minimum RSRP defined for 4G LT was minus 140 dBm. But in the later releases, this RSRP value was decreased to 156 dBm to cover the coverage performance required by the machine type communication, or we can say IoT applications. The maximum RSRP was defined for LT was 44 dBm, which is also increased to minus 31 dBm to consider the beamforming gain at the UE side. Because in 5G we are expecting that UE will be having more number of antenna ports, and that's why they will be able to receive more power in the downlink. Let's now discuss about layer 1 filtered RSRP. The RSRP measurement done at layer 1 are filtered to remove the noise impact. The RSRP range at layer 1 has a smaller reporting range compared to layer 3 RSRP. When a UE is doing or reporting layer 1 SS-RSRP, if the report quantity within the CSI report config is set to SSB index RSRP. So why it is sent to SSB index RSRP? Because 5G has multiple SSBs which can be identified by some index, and when UE is doing the SS-RSRP measurement at layer 1, so it will be decoding one of that SSB beam, and that's why the layer 1 measurements are known as beam level measurements rather than the cell level measurements. which means the SS results is linked to a specific SS or say PBCS block. The RSRP value for layer 1 or layer 3 can be represented by 7-bit payload, and the mapping is discussed in the further slides. At layer 1, SS-RSRP or CSI-RSRP can be represented from values 16 to 130. The 16 represents the measured value as 140 dBm, and this 113 represent the measured value of RSRP, which is 44 dBm. The layer 3 filtered RSRP measurements are done at layer 3, which is our RRC layer. The layer 3 does filtering similar to layer 1, and this filtering is done to remove the fast fading effect and reduce the short-term variations in the measurement results. The SS-RSRP measurement at layer 3 are useful for the handover procedures, or we can say the mobility procedures. The maximum value defined for layer 3 RSRP is 31 dBm and the minimum is 156 dBm. The full range of this RSRP has 128 entries, and these 128 entries can be represented with the 7 bits as we discussed in the previous slide. And these 128 entries covers the full range of RSRP starting from minus 31 dBm to minus 156 dBm. The layer 3 measurements can be either beam level or it can be cell level, and this can be configured by the GNB, and these measurements are sent to GNB as part of measurement report. The layer 3 measurements, the GNB provides the UE within a SSPBCH clock measurement timing, or also known as SMTC. Let's now discuss about the mapping of SS-RSRP reported value to the layer 3 or layer 1 SS-RSRP measurements. As we discussed in our previous slide, the reported value has total entries of 128, and this 128 values covers the full range of RSRP. The minimum reported value can be 0 and the maximum reported value can be 127. When we see a reported value as 0, it means the layer 3 SS-RSRP is greater than minus 156 dBm. We have also discussed in our previous slide that the minimum L1 SS-RSRP starts from minus 140 dBm to goes as maximum to minus 144 dBm. So the first 16 values are not applicable for the L1 SS-RSRP or CSI-RSRP. Those are only applicable to our layer 3 measurements. And if we go the lower part, we can also see the higher values like 125, 126 are also not applicable to the layer 1 RSRP measurements. Those are only related to the layer 3 measurements. Let's take an example and calculate the reported value to the measured value. Let's do some simple calculation for calculating the actual RSRP from the reported value. For example, the reported value for RSRP is 15 within a measurement report. And then from this reported value, we need to find out what is the actual RSRP measured by the UE in the dBm. So we have put a very simple formula where we will do a minus of reported value from the maximum value. So we are considering 57 as the maximum values and doing a minus of reported value. So from 157, if we do a minus of 15, we get a result of minus 142. And this 142 is a dB result in dBm for the actual RSRP measured value at layer 3. So this can be verified from the reported mapping table. So as we discussed in our previous slide, this table represents the reported value and the measured value. If we go on the 15, so this gives us a result of that RSRP is greater than or equal to, less than or equal to minus 142 or greater than minus 141 dBm. So our results are minus 142 dBm. This is the end of this session. Hope you like it. If you like it, please like the video and share with your friends, and please subscribe our channel for the further videos on 5G. Thanks for your time. Have a good time.